Hi, Dr. Revis here with a short lecture on bonding and hybridization. Bonding theory and bond formation follows what's called the Lennard-Jones theory or Lennard-Jones diagram, where you have two positive spin-up particles or atoms that become attracted to each other and follow a path. And as they follow that path, one of the electrons takes a spin down, flips, and takes a spin down for a negative spin 1/2. And therefore, they can now pair. That's plus 1/2 and the minus 1/2. And they will reach a point where the energy is ideal for bond formation, is at the lowest energy position where a stable bond can be formed. And when that stable bond is formed, it involves a combination between repulsive and attractive forces, and therefore we get bond formation. And what Lennard-Jones says is that the deeper the well, the stronger the interaction between the particles, meaning more stable bond. We also find that we can measure the horizontal distance from the y-axis to the bottom of the well for the bond length. So from here to here gives us a bond length. If we measure if we measure the vertical height from the bottom of the well, here to here, we can determine the potential energy or bond energy. Now, when we form these new bonds, we have orbitals that overlap. And this diagram shows you the type of overlap we can have. S orbitals only form what they form. There's no such thing as really a head-to-head or side-to-side because it's a sphere, okay? Or it's a marble or it's a ball. So it forms, and when it forms, it can only form single bonds, being sigma bonds, because that's the only interaction you can get from two marbles or two spheres interacting is a straight line interaction. Another bond that can form is S to P overlap, where you have an S orbital form of a P. In this case, the S and P will form, and it will form again an inline bond, which will be again a sigma bond. If we take two P orbitals, we can form them if they're laying on their sides, we can form what's called a head-to-head bonding, and that gives us a sigma bond as well. However, if we stand these on their sides as towers and we move them close enough, we can get overlap side to side and form pi bonds. It's one thing you want to note about overlap of bonding is that the more it's in line, the stronger the bond. In other words, if these are tilted, then the bond gets weaker. So the strongest bonds are formed in a straight in head-to-head, if you will, motion this way, or head-to-head this way, or a good side-by-side this way where they're not tilted. So that's how bonds form. Now, in order for these bonds to form, there must be something called hybridization. In other words, these electrons must be active in a plus spin-up state in order to form a bond. So what do we do then? We write out the electronic configuration diagram. That is the diagram. So we write the ground state, and in this case, we're doing carbon, but we only need to do the valence electrons, and there are 4 valence electrons in carbon. It starts at the 2s and goes to the 2p, and we get the 4 valence electrons. However, in this state, these electrons are not active to form 4 bonds. Therefore, what happens is the 2s, one of the 2s electrons, the spin down, will be promoted to a 2p. And when that happens, we get a new distribution of the electrons associated with carbon, which is why I prefer to draw these in this fashion, where you consider the base tetrahedral geometry of carbon to be 4. So we have 1, 2, 3, 4 spin up electrons sitting here. When we do this, we note that we're using an sp3. 1, 2, 3. And if we count the number of electrons around carbon, that's 4, and sp3, 1 in the s, 3 in the p gives us a 4 here. So this is what a hybridized orbital will look like. So let me repeat. We start with a ground state that looks like this. Standard ground state electronic configuration. Then we promote an electron from this 2s to the 2p, and it will be spin up when it's promoted, giving us the preferred hybridized Lewis dot structure look. This Lewis dot structure, look, now is capable of bonding with 4 different atoms and forming, for example, methane. Another look at this hybridization would be when we have the sp interaction to form sigma bonds, and we have a pp interaction to form pi bonds, which could happen in the case of CO2. Okay, so when this happens, we take the ground state, hybridize it, excite it, and hybridize it to a more excited state for bonding. We can form 4 sigma bonds, which will have sp3 hybridized, meaning that we can have 4 geometrical locations where we can put atoms around carbon, 1 in the S, 3 in the P, sp3. We just don't write the ones. This has a Vesper tetrahedral geometry, and it's known by the ABX domain classification. Note, however, that occasionally we like to write these as ABE. I tend to write ABE more often than I write AXE, but they mean the exact same thing. Also note that when it comes to hybridizing, S will max out its geometrical locations at 1, P will max out its geometrical locations at 3, D at 5, F at 7. Okay? So that's how it will look if we did hybridization of carbon. Let's take a look at another example. Let's take aluminum. We take aluminum, we will write the ground state configuration of aluminum, and we will write only the 3 valence electrons, which means we write the 3s2 and the 3p1. In this case, this is the ground state. This is how it looks in the ground state. However, in order for aluminum to bond, it needs all 3 spin up. If we want to take advantage of its all 3 valence electrons in this case, is what it would do. So we would hybridize this by promoting it to a higher energy level here, and then these electrons would then hybridize and be available to do bonding in 3 geometrical locations. And that's why we like to represent the aluminum in this fashion, just to show you what it'll look like. So these electrons spin up. By the way, these half spins are the same as the double-headed arrows. They mean the exact same thing. I just like to draw half arrows. So we get in this case now, we'll have an sp2 hybridized look. And that would give us sp2 will look like this in a classical Lewis dot structure of a hybridized look. And we take that hybridized look, sp2, and if we'd like, we could bond with 3 other atoms. I just pick iodine here, for example, and we get an sp2 hybridized AX3 domain. So we have 3 sigma bonds here, no lone pair, and we can look at this hybridized promoted state, and we don't see any pairing, so there are no lone pairs. sp2, sp2. This we memorize as Vesper trigonal planar because it has that geometry, and it's an AX3 domain class which we simply learn how to name. So to repeat, we take the ground state of aluminum, we promote this spin down -1/2 to a +1/2 excited state, and now we have 3 electrons available for bonding. Let's do one more here. Phosphorus with 5 valence electrons. We've already drawn out the Lewis structure of a potential compound we can make, just to reiterate what it might look like when we use it. But let's just start with the ground state of phosphorus to show you how we got here. We have the ground state of phosphorus. It's going to be a 3s2 and a 3p and a 3p3. And so, in order to help us to do chemistry, we're going to take, or bonding chemistry that is, and follow the Leonard-Jones theory. We would take 1 electron from the 3s and we would promote it to the 3p. And this is what we would get. Now, at first inspection, say, well, why do we do that? We already have a paired here, we have a paired here. When we promote this, this allows these orbitals to operate in a degenerate fashion, meaning that we have better opportunity for bonding here and for using these lone pairs for bonding as needed to create octets. Okay, so we promote these. We take this electron, we promote it to here. You could put it in the first one or the second one. It tends not to really matter when you're doing this on paper. The electrons know exactly where they go. But when it's excited and promoted, we get this look, and this is what we see if we draw out the preferred, or at least the way I prefer to draw a Lewis dot structure. It's not to just group them, but to put them in a hybridized pattern, and this is what a hybridized pattern will look like, which means it's SP3. So we use SP3 to get here. And we know this SP3 because we use 4 geometrical locations, 1 in the S, 3 in the P. And if we write the ABA domain, that's going to be an AX3E. Why? A is the central atom. X are the attached groups around the central atom. And when we talk about attached groups, we're talking about those that are bonded. And there would be 3 if we bonded it in the fashion shown here. Just to show you, this would be 1, 2, 3 bonded. And E would be the electrons shown here. That is not just electrons, but the lone pair electrons. So let me correct that. It's not just electrons. It is lone. It's the lone pair electrons. So we have 1 lone pair electrons for E here. So this is what happened when we took this hybridized look of fluorine and bonded it with a hybridized look of phosphorus. And here it is, 3 sigma bonds, 1 lone pair, which we can see in a hybridized look. sp3 hybridized, we memorize that it's Vesper trigonoplanar pyramidal, and we have ABX3E domain classification. So let's reiterate. Bonding theory teaches us that 2 spin up electrons will find each other. 1 will flip to a minus. They will find a low energy position with ideal bond length and ideal energy. Overlap of s orbitals. When they overlap, they only create sigma bonds. Overlap of s and p, sigma bonds. Head to head, p orbitals, sigma bonds. Side by side will be pi bonds. And always remember, you can't have pi bonds until you have sigma bonds. All right, there you have it.